talk about DNA origin, and mostly about application in structural biology. So we do a short introduction about the method of the DNA self-assembly. So we use a long sequence string of DNA from M13 page. So because we know the sequence of the DNA, so we can design some single string of short oligo, which can be complementary of the different part of the long single string. So by this way we can do some motif. So because we can name some different parts of the long single string only by designing the short oligo in yellow. So we can short oligo are active. Okay, so the short oligo are acting like staples to fold the DNA in a specific shape. So in 2006, the first DNA origami, the 2D DNA origami was made by Paul Riemans, where he used a long single strand engraved DNA from the phage and M13 phage, which acts as a scaffold, and by designing several staples, short oligonucleotide staples, to cross-link the DNA, can make a 2D array of parallel DNA to make a 2D shape, and by controlling the size of the double helix, you can make a shape in 2 dimensions. So this was the first generation of DNA, and in 2009 in the William Shih lab we made a new generation, the 3D DNA origami, where we can link the staples from that at long range distance in order to make a 3D DNA shape. So this was done in 2010, and to do it we use a software called Nano, where, for example, for a short 6-helix bundle DNA nanotube, we have here in blue the scaffold, where we do the sequence, and we can design the staples, the short oligonucleotide, to have a shape like that, so a 6-helix bundle with a short nanotube. So I made a movie to show you how it's work in solution. So once we have the design, we order the oligos, a set of oligo to the company, and we mixed everything in salt with a specific buffer. And at very high temperature, around 80, 85 degrees, everything is unfolded. And by decreasing the temperature until room temperature, or 25 degrees, over a day or over a week, depending on the complexity of the object, we can have the self-assembly of the molecule. And if you look the red staples, it's cross-linking 2 different helix. So by this method, we can make different shape in 3 dimensions, so like a tube or a ribbon, a ring, a sphere, and cool things of this kind of structure we can see it under TM quite easily. So we made since the development of the 3D DNA origami, we made different methods in order to get very high yield of synthesis with a high purity. We can also wrap the nanostructure with different kind of molecule like a PEG in order to get a very high biocompatibility, and we can also label the origami with different particles by controlling the stoichiometry and the orientation of the particle, like a gold particle here. And also one of the advantages of this technology is that we can have a dynamic object. So I will talk about that later. So few applications. So one of direct application is for drug delivery, where we can use it like a kind of a nanorobot, where we can do some drug delivery, or like nanopore in nanophotonics. And for the rest of my talk, I will talk mostly about the application in structural biology and in biosensing. So in structural biology, because one of the challenges today is to solve the structure of membrane protein, which is involved in most of the biological process and is involved in almost all the diseases. So that's why membrane protein are one of the prime target for the drug discovery, with 50% of the drug on the market are targeting membrane protein. So to do some new drug design to get a new drug, we need to know the structure of the protein before. But to solve the structure of membrane protein, it's very challenging. And we don't know a lot about the structure of membrane protein, because if we look in NMR, the proteins are in general too big to be solved by NMR, and too small to be solved by electron microscopy, and very dynamic. So it's very hard to get a nice crystal to solve the structure of membrane protein. So we use a strategy to solve the structure of a membrane protein by using DNA origami. So we made a 6-helix bundle nanotube. It's almost 1 micron in length. And the advantage of this kind of nanostructure is at very high concentration, we can have a liquid crystal. And the liquid crystal is magnetic field and have a dipolar coupling, so we have a splitting of the deuterium, for example. So how it works, we mix the membrane protein with the nanotube. And due to the electrostatic field of the negatively charged nanotube, we have a specific orientation of the membrane protein in the magnetic field. So by this way, we have an anisotropic solution, and we can extract some specific structural constraints. And we can have a dipolar coupling for each residue of the protein, and we can solve the structure of big membrane protein. So it's what we did for the UCP2 membrane protein, which is a proton carrier. It's with a 6 transmembrane helix, and we use it to solve the structure, which is one of the biggest structures solved by NMR. And most recently, we use the same strategy to solve the structure of a GDP carrier, which is from mitochondria. And we also probe the dynamic of the receptor, where we can follow the binding of the GDP through the pore of the carrier. So the second study we talked today, it's about biosensing and in single molecule. So one of the challenges is to follow the complex of molecule, for example, here's molecule A and B. So in order to do some single molecule threat or biosensing photonics. So for different applications, that's one of the challenges to control the distance between particles. So we made a device which we call a Nano Compressor, where we can attach on the device the molecule A and the molecule B, and we can control the distance on the sides of the device, which acting like a driver, where we can keep it open or closed. And also we can use it for biosensor, where we can attach on the two arms of the device a pair of dye quencher in order to have a readout after a stimuli which we can detect the fluorescence. So what we did is we made a device with each arm of the device. It's about 10 helix bundle, where in blue you have the scaffold. Each arm are linked by the scaffold in blue. Here you have an oligo to attach the label with the molecule, the corner, and the bar to control the open and the closed state of the device. So from the open state to the closed state, we can control the different state by adding some oligos which will lock the device in different conformation. So from the open state to the closed state, we can see on the agarose gel, and under TEM we can see the number one it's open and getting closed. So the closed device is running faster inside of the agarose because the volume is small. So we can see the different states. And so technically we can label the device with any kind of molecule. So for example, if we take a gold particle with a single strand DNA, where on the device we have the complementary sequence, if we add it solution, we can have the label of the device, and we can control the different states of the device as well. So as a proof of concept, we use the GFP, and because if you split, you know, but if you split the GFP in two, and if you do the complex of the two split GFP, you can get the fluorescence back of the GFP. So what we did is to label each part of the GFP with a single strand of DNA, which is complementary from one part or another part of the device. And by making the complex, we can follow the fluorescence of the GFP. So we have the device. When we keep it open, we have under TEM, we can follow the angle between each arm. So it's around 60 degrees. And if we look here, we don't have any fluorescence. But when we force the device to close, we can restitute the fluorescence. And we can see the device. The angle is going to around 10 degrees. So we can control the distance between two molecules, and we use this kind of device to act as a biosensor, where we have two dyes actually. And when the two dyes are very close in distance, it's quite dark, no fluorescence. But when the two dyes are far apart, there are fluorescence of one of the dye. So, and we can drive to open the device by a different stimuli. For example, we use a J quadruplex here to follow the concentration in potassium, or the presence of enzyme or microRNA. And when in presence of potassium, we can force the device to be open. So under TM, we can see the drastic conformational change of the object, and we can also have a readout in fluorescence when we see an increase in fluorescence. And we made it for different molecules. Okay, so I just want to thank the people working in Montpellier on the project, and also the CBS with Manu and other Manu for fluorescence, and Patrick Bon for the electron microscopy, and also the William Shi and James Shu from Boston. Thank you.
wondering if you could comment on the status of being able to build things like this inside cells where, where it's so, noisy, and is there any hope for that?
Yeah. Since we know now we can fold the object, because what we do is we start to fold the object, to start first to unfold the DNA and after to go down in temperature. So we start in general at 80 degrees and we go down to 20 degrees over a day or over a week. But now we know that we can do it at constant temperature. So far it's around 40 degrees. But we hope that at some point 30 degrees will be possible. But there is a field now trying to fold objects inside of it, so that would be a big deal. Yeah.
Over here, I have a question. So this shape changing, I was wondering, is it sort of a two-state system? So is it sort of like most simple proteins that fold? Is it open or closed? Or can it be sort of in any particular? You had sort of a movie that was very suggestive of it actually being in several states. The movie, I guess, is a superposition of EM slides. Right?
Yeah, exactly. So, it's mostly we can control. We can go from open states, add a set of oligo, go to a second step, add another step of set of oligo, and go to a third state. But each time you have to add some oligo instead of the solution.
So for one particular set of oligos, it's sort of either in the open or in the closed. I understand there are several closed states because it depends on how you design it.
Yeah. Last question.
What method are you using for the GFP DNA conjugation?
I'll say it.
In conjugating the single-stranded DNA to your GFP?
What
conjugation chemistry?
Yeah, we use a cysteine free from the GFP. And just by, so it's a cysteine free, we add biotin, streptavidin, and biotin on the oligo. So it's a sandwich between biotin, streptavidin.
All right, thank you, Gaëtan. So we're going to move on.